Hello everyone, my name is Arif Jafari, and in this video I'll try to give you the basic ideas of how to define and train a simple deep neural network in PyTorch. We will develop a simple feed-forward neural net step by step for the handwritten digit classification task. The dataset of this task is called MNIST, where you can find some of the sample of this dataset here. So this dataset contains 60,000 training samples and 10,000 test samples, where each of them is a 28 by 28 grayscale image of handwritten digits. And we will have 10 classes, each class for one of the digits. And we're going to develop this simple feed-forward neural network. As you can see in this figure, this network has an input layer, an output layer, and also two hidden layers. The input size is 784 and the output size is 10, equal to the number of classes. And each of the hidden layers has 1000 neurons. So we need to vectorize the input images before passing to the neural network. So by vectorizing or flattening an image, we mean consider that we have a matrix, which is our image, 28 by 28. By flattening, we just transform the representation of this matrix from 2D into a 1D vector by just concatenating each column of this image in a very large vector. So if the size of the image is 28 by 28, the size of this vector would be 784, as you can see here. So in general and in the most basic form for implementing a neural network in PyTorch, we need to implement 6 steps. Actually, these 6 steps are not something standard. I just defined them, or at least these are the things we will do in this tutorial. But always I'm just following these 6 steps to implement a neural network. In the first step, we need to import libraries and set up necessary parameters. In the second step, we should prepare data for training. In the third step, we should define the neural network we want to train. In the fourth step, we will define 2 important functions, train and evaluation functions, where we will use them in the next steps. In step 5, we will define the main loop of training the network, and in step 6, we will evaluate the trained model after we get it from step 5. So before starting first step, I would like to talk a little bit about the programming environments that I'm using here. As you might know, most of the deep learning projects develop in Python these days, and because of intensive computations of deep learning models, we need to use GPUs to accelerate our computations during training a deep learning model. So you might not have an appropriate GPU or graphic card for training a neural network on your computer, but there's a service by Google which is called Google Colab, which provides a Python notebook environment for developing Python codes plus a free GPU or TPU access in order to accelerate the deep learning researches. To access this service, you can just, after logging to your Google account, you can just go to collab.research.google.com, And here you can just start a new notebook and write your Python code here. And by pressing this button, you can run your code. Okay. But before start writing your code, you need to add GPU to your project. For this purpose, you need to go to runtime, then change runtime type, and then select GPU from here and save it. Now you just add the GPU to your notebook, and if you start writing your code in this notebook, you will have access to both GPU and CPU in this notebook. But I just wrote all the codes of this project here, so I'll just go to explain it in this notebook. Now we are ready to develop our code. So in the first step, we will import the necessary libraries and set up some training parameters. As you can see, the basic and important libraries we have here are NumPy, PyTorch, Torch Vision, and also the matplotlib. So NumPy is a fundamental package for scientific computing in Python. It provides multidimensional tensor objects and also the linear algebra operators over these tensors on CPU. PyTorch, on the other hand, is an open source deep learning platform, as you know, and it is very look like NumPy in terms of giving you access to multidimensional tensors and linear algebra operators. But it also includes several additional features like supporting GPUs and other acceleration hardwares, as well as other efficient tools for deep learning researches. Torch Vision library is a part of PyTorch, contains all the important data sets of computer vision, as well as general models and transformations in the field of computer vision. So we use it here to access the MNIST datasets and also the necessary transforms that we want to apply on this dataset. Matplotlib is a powerful tool for visualization in Python. You can create several advanced plots using this library. So we import our libraries in this cell. We can just run it by pressing this button. And then we can go to the next step. In the next cell, we define the device which we want to run our model on it, CPU or GPU, and also we initialize the random seed. In this line, we detect if CUDA framework has been installed on this machine and the GPU is available or not. So based on that, we can detect if we want to run our model on GPU or CPU. By the way, CUDA is a parallel computing platform developed by NVIDIA, and it is used for developing models which can be run on NVIDIA GPUs. PyTorch uses this platform to run a model on a GPU. So this part of the code will detect if CUDA is available or not, and if it is available, the device would be CUDA, otherwise it would be CPU. So we can just run it by pressing this button. Now we can define some runtime parameters like the input and output size, dropout ratio, and also the number of training epochs. Now we are ready for data preparation. This step can be as easy as we can see in this tutorial, or it can be very sophisticated. In real-world problems, most of the time data is not ready to use for training a model, and you might need to do several steps like extracting and washing data. By washing, I mean removing the bad samples. Also, you might need to normalize data and so on. But for famous datasets like MNIST, always you can find clean and ready to use versions of them in deep learning packages like PyTorch. In the end of data preparation step in PyTorch, we need to create two types of specific objects for each dataset. Dataset and data loader objects. For each of datasets like train, test, and dev sets, we need to create a pair of these objects. The dataset object contains or have access to all data samples in the dataset, and it has some specific functions to control the data, like returning the size of dataset or returning a specific data sample by passing its index. Also, one of the duties of this object is applying transforms on the data samples. Transforms are a set of functions which apply on the data samples when we want to retrieve them from the dataset objects. For example, we have two transform functions here, one for creating data samples from image objects to PyTorch tensor objects, and other for normalizing the pixels of the images. The other important object is data loader. The duty of this object is handling mini batches and shuffling data during training. We pass the dataset objects that we created before when we constructing the data loader object. Then it handles generating mini batches and random shuffling data during training. So as you can see, we created two data loader object here, one for the train set and one for the test set. Now we can plot some of the samples in the dataset. You can find its code here. And as you can see, the samples are like this. Now we are ready to define our model. Here we define the neural network model that we want to train it. To define a neural network in PyTorch, you need to write a specific class, which is called the model class, and it inherits the torch NN module class. In the constructor of this function, you can define the layers of the network. For example, here we have three layers of FC1, FC2, and FC3. Where FC is the acronym for fully connected. The fully connected layers or linear layers can be found in the NN package of PyTorch. So each layer in PyTorch has an input and an output. For example, this linear layer here has an input of 784 and output size of 1000. And also you can see the other layers and their input and outputs here. Later you can define the other kind of layers like the convolutional layers or recurrent layers like LSTM layers to define the convolutional neural networks or recurrent neural networks. This class also has a specific function called forward function, which you can see it here. The forward function gets input data in the form of a tensor object of PyTorch from input and applies different layers of the network on it. For example, this x here is the input of the function, and it should be in the form of PyTorch tensor. So in the first line of this function, we flatten the input images, and then we pass the flattened images to the first layer of the network. Then the output of this layer goes to ReLU nonlinearity, and then it's passed to the dropout. So the output of the first layer goes to the second layer. The same procedure will happen here again, and in the end we just pass the output of the third layer to the softmax function, and we return the output of the network at the last line. Now we prepared the dataset and also defined the network. In the next step, we need to train our network on training dataset and evaluate its performance on the test dataset after training. For that purpose, in step 4, we need to define two functions, the train and evaluation functions. The train function, as you can see here, gets a model which is an instance of the network class we defined above, and also a data loader which will be the train loader from input, and train the model on the given data set or data loader for one epoch. In the first line of this function, we define the optimizer that we want to optimize our network using that. Here we defined Adam. To defining an optimizer, we need to pass all the parameters of the network, which will be the weights of the network here to the optimizer. Then it can just preterm the weights later. Also in PyTorch, the models have two states, the train state and the evaluation state. So for training a model, we need to put it in the train state. Then we have some intermediate parameters here. After that, we have the training loop here, where we'll just iterate over the data in the data loader, and each time gets one mini batch from the data loader. After getting the mini batch, it puts the data samples and also the labels on the device which we defined above. Then we call the zero grad function of the optimizer to set all the gradient matrices in the network equal to 0. And then we pass the images to the model to get its output. So by passing the images to the model, actually we call the forward function of the model or the network we defined above. So the images will replace by this X and pass all the layers, the network layers that we defined here, and then the output will return in the end. Then after getting the output of the model, we can pass it to the loss function here, cross entropy loss function, and then we can calculate the loss between the output of the model and the target labels that we have from the data set. After getting the loss of the network, we can call the backward function of the loss. So here, by calling the backward function, the backpropagation procedure will happen, and PyTorch will calculate all the gradients of the weights and save them in the network. Then we call the step function of the optimizer. By calling this function, the Adam optimizer, which we defined it above, will use the gradient tensors calculated in the previous step to perturb the network's weights. Then we accumulate the amount of loss in each step and count the number of steps. Then by using these information, we can return the average loss of this epoch in the end of the function. So as you saw, this function trains the given model for one epoch. The next function is the evaluation function, which gets a model instance and a data loader, which will be the test loader here from the input, and evaluates the performance of the model on the test dataset. So as I mentioned above, the PyTorch models have two states, the evaluation state and train state. So here we need to set the model's state to evaluation. Then we have two intermediate parameters again. This line will tell the PyTorch to not to calculate the gradients when we pass the data to the model. Then again, we have a loop over the data loader to get the data in mini batch each time. So after getting the data samples, we put them on the device. Then we send the images to the model to calculate the output. After that, we can calculate the test datasets loss and accumulate it in this intermediate parameter. Then in the next line, we can find the predicted classes for each images by getting an argmax over the output vector of the model. As you know, the output of the model is a vector with 10 elements where each element shows the probability of each class. So we can calculate the argmax to find the class with the maximum probability as the predicted class for that image. Then in the last line of the loop, we can accumulate the number of labels which predicted correctly. So after the loop, we can calculate the average test loss in this line, and then we can calculate the accuracy of the model by just dividing the number of correct labels with the total number of data samples in the data set. Now we have everything to train and test our neural network. In the next two steps, first we train the network and then test it over the test dataset. Here in this cell, we define the main loop of training, which iterates on the number of epochs and call the train function each time to train the network for one epoch each time. But before that, in the beginning of the cell, we get an instance of the network class that we defined above, and then like the data samples, we put it on the device. Then we call the main loop of training here to train the network for several epochs. Now for training the network, let's first run all these cells from the beginning to be sure that we run all of them. So you can do that by just pressing Shift and Enter button together. I'm just running all the cells. Now step 4, and now we are in the step 5. So if I run the step 5, the cell in the step 5, our network will start the training. At the moment we are in the epoch 1 from 100 epochs. So the first epoch finished, and the average loss of the epoch is 1.8. Now we got the results of the second epoch. It is 1.7, and we need to wait until the last epoch. But I had run this model before, and in the sixth step we can plot the behavior of the loss function during the training, and also we can just print the accuracy of the model. If you train this network for 100 epochs, you should get accuracy around 98 percent on MNIST test set. So here in this cell, we just calculate the accuracy by calling the evaluation function here and passing the trained model from the previous step and test loader to this function.